Hi, my name is Bart Jansen, and in the next 25 minutes, I will show you why bridge depth characterizes which structural parameterizations of vertex cover admit a polynomial kernel. This is joint work with Marin Bougeret and Ignasi, both at Université de Montpellier. This work deals with data reduction with guarantees for NP-hard problems, or in other words, kernelization. Let me formally define what a kernelization for a parameterized decision problem L is. It's an algorithm that transforms input parameter pairs into new input parameter pairs. It's efficient, it does its transformation in polynomial time, and preserves the yes-no answer to your problem. And most importantly, there needs to be a size bound such that both the size of the new instance and the parameter value of the new instance are bounded by some function that depends on the old parameter alone. This function f we call the size of the kernelization. And if it's a polynomial bound, we call it a polynomial kernelization. Intuitively, kernelization guarantees that inputs which are large compared to their complexity parameter can efficiently be shrunk. We investigate kernelization for the fruit fly of parameterized algorithms, the vertex cover problem. So the input is an undirected graph, an integer k. The question is if we can find a set of k vertices such that each edge has at least one endpoint in the set. And here we see a vertex cover of size 7. Note that the size of a vertex cover we can also think about as the vertex deletion distance needed to get from our graph to an edgeless graph. Because if you take a vertex cover and delete it from the graph, the resulting graph doesn't have any edges anymore because they were all covered. Good. With this interpretation, let's talk about kernelization for this problem. So based on the classic Nemhauser-Crowder theorem, it's known that there's a kernel with 2k vertices. A polynomial time algorithm can reduce an instance with parameter value k to an equivalent one on at most 2k vertices. And if you rewrite this a little to make it easier to compare to some of the things we're going to see, we can say that a polynomial time algorithm can reduce any input to an equivalent one that has at most twice the vertex cover number many vertices. On the one hand, this is a very nice result. On the other hand, the guarantee that you reduce the graph to at most twice the minimum vertex cover size many vertices can be meaningless on graphs such as paths, because for a path, twice the minimum vertex cover size is the entire graph size. So how can we get kernelizations which give good guarantees even when the minimum vertex cover size itself might be large? Well, we can use other complexity measures of our graph. For example, the feedback vertex number of our graph, the vertex deletion distance to a forest, an acyclic graph. So for the graph we see, which has a minimum vertex cover size of 7, already these 3 highlighted vertices are enough to break all the cycles. So the minimum feedback vertex size of this graph is only 3. Since this parameter gives smaller values, we would be able to give better preprocessing guarantees in terms of this parameter. Indeed, what happened? Almost 10 years ago, with Hans Bodlaender, I showed that a polynomial time algorithm can reduce any instance of vertex cover to an equivalent one whose number of vertices is cubic in the size of a minimum feedback vertex set, in the size of the deletion distance to a forest. This then spawned a long line of follow-up work that basically asked, how much can we generalize from forest? If we take smaller parameters because they measure deletion distance to richer graph classes, can we get polynomial kernels in terms of such parameters? And after forest, the case of graphs of max degree at most 2 were done. Pseudo-forest, where every component has at most one cycle. Quasi-forests, where every component has a feedback vertex set of some constant size d. Graphs of constant tree depth were considered. Also, the elimination depth to forest was considered earlier this year. So all of these are measures of complexity for a graph by taking the number of vertex deletions to get a graph of, say, constant tree depth, or to get a graph of constant elimination depth to a forest. Now, what we do in this talk is introduce the notion of bridge depth that generalizes and captures all of this previous work. So, our results are as follows. We introduce a new graph parameter called bridge depth. We do it by a recursive definition similar to tree depth. And then we prove that if F is a minor closed class of graphs, under the standard complexity assumption that NP is not in cone P poly, the vertex cover problem parameterized by vertex deletion distance to F has a polynomial kernel if and only if this family F has bounded bridge depth. So if there's a constant that bounds the bridge depth of all graphs in F. So effectively, graphs of bounded bridge depth form the ultimate tractable generalization of both forests and bounded tree depth graphs, which were considered in earlier work. This generalizes all deterministic kernels for vertex cover known before. And our proof relies on an excluded minor characterization of bridge depth and connecting its graph theoretic properties to notions called blocking sets, which have been used in kernelization before. So to define bridge depth, let me first define tree depth so that we can later vary on this definition. Intuitively, tree depth measures the depth of a process that eliminates the graph by removing vertices in rounds. There's a formal recursive definition. The tree depth of G is 0 if G has the empty vertex set, G is empty. If the graph is connected, then we try all ways of removing one vertex V and taking the tree depth of the resulting graph. And the minimum out of all of these, we add 1 to that, and that is the tree depth value. If the graph is disconnected, then the tree depth is simply the maximum over its connected components. So you can think of this alternatively as we have to eliminate the graph until we get to an empty graph. And in each round, we can delete one vertex from each connected component. And we have to see what the minimum number of rounds is by which to do this. So if you do it to this graph, then the first round would eliminate this vertex. The second round eliminates these. The third round eliminates these. And in the fourth round, we're done. So if you then label the vertices with the round in which they were eliminated, this is what you get. And it shows you that the tree depth of this graph is at most 4. Note that tree depth is at least tree width and doesn't increase when taking minors. And also, a connected graph has a single vertex whose removal decreases the tree depth. So let me now define bridge depth. It measures the depth of a process that eliminates the graph by removing trees of bridges at once. So let GCB be defined as the graph obtained from G by simultaneously contracting all bridges. The bridge depth of G is defined as follows. It's 0 if G has the empty vertex set. If your graph is connected, then first we contract all the bridges. Then we try all ways of deleting a vertex and checking the bridge depth of the result. We take the minimum out of all options and add 1. And if your graph is disconnected, then we take the maximum over the bridge depths of the connected components. So here we can think of this as we have to do a process that eliminates the graph, not by deleting one vertex at a time, but every time contracting all bridges and then deleting one vertex in each component. So if we do it to this graph, then we have to start by contracting the bridges. And recall that a bridge is an edge of the graph whose removal strictly increases the number of connected components. So all of these highlighted edges are bridges. If we contract all of them, then we get this graph, and here we eliminate one vertex from each component. So this one, then we contract all the bridges again, and now we eliminate one vertex from each component, and we're done after 2 rounds. So annotating the vertices with the rounds in which they're eliminated gets us this decomposition and shows that the bridge depth is 2. Tree depth is at least bridge depth is at least the tree width, and also the bridge depth values don't increase when taking minors, which can be shown by some elementary argument about what happens to bridges when doing minor operations. So a connected graph has a tree of bridges, such that if you remove it and the incident vertices, then the bridge depth strictly goes down. Now, to use bridge depth to kernelize the vertex cover problem, we relate vertex covers to bridge depth via the notion of blocking sets, which will be explained next. And actually, a lot of the work we do is to characterize the graph theoretic implications of bounded bridge depth. So we'll introduce the notion of blocking sets and the notion of neckless minors, and show that three things are graph theoretically equivalent. A minor closed family having bounded bridge depth, having bounded size on minimal blocking sets, and having bounded length of neckless models. First up are blocking sets. So let alpha of G denote the maximum size of an independent set in G. This is a maximum independent set, its size is 6. A vertex set is a blocking set if removing that set from the graph strictly decreases the size of a maximum independent set. So this red set is not a blocking set because even without it, we can make an independent set of size 6. But this blue set is, because if we're not allowed to use the blue vertices, then the remaining graph has only a maximum independent set of size 5. A blocking set is minimal if none of its proper subsets are blocking sets. So, how do blocking sets relate to kernelization for vertex cover? Historically, they've been very closely tied together. On the one hand, all known kernels are for deletion distance to families F whose minimal blocking sets have constant size. On the other side, if F is closed under disjoint union and contains graphs with arbitrarily large minimal blocking sets, you can make a kernelization lower bound under standard assumptions. So this leads you to the question, is a bound on the sizes of minimal blocking sets for graphs in F sufficient to get polynomial kernels for vertex cover parameterized by distance to F? And as a byproduct of our work, we answer this question for minor closed families F. The answer turns out to be yes. So earlier this year, Holz, Crutch, and Peters showed that there's classes F which are not minor closed, where this relation doesn't hold, but whenever you have a minor closed family with bounded minimal blocking sets, you do get polynomial kernels. And in particular, such families have bounded bridge depth, which leads to the result. So let's now see some of the connections between bridge depth and blocking sets. Consider the following graph. We start with a chain of n vertex disjoint triangles in a sequence. And out of this chain, we remove the very first and last vertex. And we call the graph we get in this way delta n. This is part of a gantet used by Fomin and Stroman. Observe that the independence number of this graph is equal to the number of triangles, because we can pick one out of each triangle and no more. The n bottom vertices of these triangles form a blocking set, because if we're not allowed to use any of these vertices in an independent set, then there's a matching of size n-1 on the remaining vertices since we chopped off the ends, and this means that we can get at most n-1 vertices in an independent set when not using any of the bottom ones. And this blocking set is minimal because if we give up one vertex and allow it to be used, then we can make an independent set of size n by picking this bottom vertex and pushing towards the vertex that we use at the bottom from both sides to get one vertex out of each triangle in our independent set. So then we see that this graph delta n has a minimal blocking set of size n, which we'll use later. We connect blocking sets to bridge depth via necklace models. A necklace model of length m in a simple graph is a sequence of disjoint connected vertex sets such that each of these sets has at least two edges to the next set. So you have your graph and we have our numbered vertex sets, and each set induces a connected graph and has at least two edges to the next set in this sequence. Now, let me first show you how necklace models relate to this graph delta n. If a graph G has a necklace model of length t with t+1 sets, I claim that it contains delta n as a minor, where this n is roughly t12. To do that, we're basically going to build a minor model of delta n out of this necklace model. And we take these sets in pairs. And we pick one of these sets and we partition it into two connected vertex sets, each of which has an edge to the next vertex set. And the next vertex set becomes a singleton set. If the first set of the two has a single vertex incident on both connections to the next set, and instead of splitting that set, we split the set that it's connected to into two vertices that will be part of our triangle. And in this way, out of each pair of successive sets, we can define a minor model of a triangle. so that indeed, if we had a necklace model of length t, which contains t plus 1 sets, then we find a sequence of t plus 1 over 2 triangles in a chain as a minor. Right? This is what the minor model looks like. And together with the fact that this delta n has large blocking sets, we now see the following. If we have a minor closed family of graphs that contains some h with a necklace model of length t, then we see that h has a minor, which is delta t by 2, and this minor is again contained in F because F is minor closed, and this graph H prime has a minimal blocking set of size t by 2 because the number of triangles in your path of triangles was equal to the size of a minimal blocking set. So this shows that if you have a minor closed family with a long necklace model, then some graph in that family has a large minimal blocking set. This proves the first implication in this chain that will become the equivalence. By contraposition, if all minimal blocking sets have constant size, then the necklace models of your graphs in F must also have constant size. So next up, we're going to explore the implication that shows that from a bound on necklace models, you can get a bound on bridge depth. The main graph theoretic property we're going to use now is this fact that if my graph is bridgeless and connected, then any two maximum length necklace models must intersect. So let's prove this by contradiction. Let's assume that I have a graph whose maximum length of a necklace model is 4, so 5 sets in a model, and assume that there's two vertex disjoint models of 5 sets each. Out of this, we derive a contradiction. So let's pick a vertex S in the first set of the top sequence and a vertex T in the first set of the bottom chain. Since our graph is bridgeless and connected, Menger's theorem implies there's two edge disjoint paths between S and T. And we can trim this to become two edge disjoint paths that connect something in the first chain to something in the second chain with no interior vertices belonging to either chain. Now we do a case distinction, and in both cases get a contradiction. Suppose that one of these paths that we get, it attaches to a set on a chain that's not the middle set of the chain. So the blue path here attaches to the middle set of the top chain, but not to the middle set of the bottom chain. Then out of this, we can straight away define a new necklace model with more sets than either of the ones we had, contradicting the assumption that these were maximum length necklace models. And the way we do it is by simply taking the longest part of the top chain before this attachment point, so say the left side, the longest part of the bottom chain getting to the attachment point, so here the left part, and we merge these two sets together with the path into one connected set that thereby gets two edges to both of its adjacent sets in this chain. And since now we went from two chains with 5 sets each to one chain with 6 sets, this is our contradiction. Now suppose that both the paths that we get attach to exactly the middle sets of both chains. Then we can do a similar operation where now we absorb the interior vertices of these paths into the middle set for the top chain. And if we do that, since there were 2 of these paths, this set now gets 2 edges to the next set, which was the original bottom. Again, we've gone from 2 chains on 5 sets each to 1 chain on 6, and we get our contradiction. So we see that in a bridgeless connected graph, any 2 maximum length necklace models intersect at a vertex. Now, by known applications of Oede's positive properties for models of planar minors, this implies the following. If you cannot pack 2 vertex disjoint length t necklace models in your graph, then there's a vertex set whose size depends only on t and the constant 2 that intersects all such models. So let's introduce some notation. Let nm of G denote the maximum length of a necklace model in G. And by the property we just proved, if your graph is connected and bridgeless, then there is a vertex set whose size depends only on nm of G, whose removal strictly decreases nm of G. So I can remove a vertex set, thereby strictly decreasing the maximum length of a necklace model. Let me now show you how all of this implies a relation between bridge depth and the length of necklace models. I claim that any graph can be reduced to an acyclic one by a process with a bounded number of rounds, a number of rounds depending only on the maximum length of necklace models in G, where each round consists of the following two things. First, contracting all bridges, and second, removing a small vertex set. Observe that if we contract all bridges, then this doesn't change the bridge depth, by definition, because bridge depth was defined on the graph on which we contracted all the bridges anyway. And after having contracted all the bridges, in each component, each pair of maximum length necklace models intersects. So out of each component, we can remove a vertex set whose size depends only on the maximum length of necklace models to strictly decrease the maximum length of necklace models. So after nm of g many rounds, we got to a graph that doesn't have any necklace models anymore. Since any cycle already gives you a necklace model of length 1, after this many rounds, we got to an acyclic graph. And an acyclic graph has a bridge depth 1. So the fact that you can do nm of g many rounds that delete a constant number of vertices essentially implies that the bridge depth of your graph is bounded purely by a function in the length of necklace models of your graph. And this brings me to the second implication. In our chain of equivalences, we've just seen that if the length of necklace models in your graph is constant, then the bridge depth of all graphs in your family is also constant. Now, the last step of this equivalence is an induction that I don't have time to show you, which proves that a bound on the bridge depth also gives you a bound on minimal blocking sets. But then all these graph theoretic properties turn out to be equivalent. Of course, for this talk, it's then interesting to tie that into the algorithmic consequence of having polynomial kernels and lower bounds for kernelization from lower bounds on minimal blocking sets. Let me briefly talk about the application to kernelization out of these graph theoretic properties. So the input to the kernelization is a vertex cover instance and a vertex set whose removal gets you a graph of constant tree depth, say eta. You can find such a set by a polynomial time approximation algorithm if you don't know one. As output, we want an equivalent yes-no instance of vertex cover whose size bound is polynomial in the size of this deletion set X. And is going to be an inductive scheme. What we do first is reduce the number of connected components of the graph outside this deletion set. So this is a potentially large graph, but one that has bounded bridge depth. And using the fact that bounded bridge depth implies a bound on minimal blocking sets, ideas from the existing kernels easily give you a reduction rule that bounds the number of connected components here to polynomial in the size of the deletion set. Then we can zoom in on each component, and we know that a component of bounded bridge depth has a tree of bridges, here in red, whose removal strictly decreases the bridge depth of the graph. So if the bound was at most eta, then removing this tree of bridges shrinks the bridge depth to at most eta minus 1. Then the main technical work in the kernelization is to apply local reduction rules that shrink this tree of bridges to one whose size is polynomial in the deletion set. And here we have to very carefully take into account the connections between the deletion set and the interior of this bounded bridge set graph. Right, so we shrink this component to shrink the tree of bridges. And then comes a step where we take out of each component the vertices of this depth decreasing tree of bridges, and we move those vertices into our modulator X prime. This then ensures that the graph outside the deletion set has bridge depth at most eta minus 1, improving from the bound eta we had. And since the number of components was polynomial in X, and the size of each such tree is polynomial in X, we get that the size of our new deletion set X prime is still polynomial in the size of X. So now what we do is we effectively recursively kernelize the problem, but now with this larger deletion set and this smaller value of eta. And when eta hits 0, it implies that there's no vertices outside X anymore, and then the kernelization is done. So let me conclude. The main result of the paper is that vertex cover parameterized by deletion distance to a minor closed family F has a polynomial kernel if and only if this family has bounded bridge depth. This generalizes all known deterministic polynomial kernels for vertex cover and implies that for minor closed families, a bound on blocking set sizes is sufficient to yield polynomial kernels. Now, one important class of graphs which isn't captured by this theorem is the class of bipartite graphs, which is not minor closed, but for which a randomized kernel exists. Our main open problem is therefore to make a characterization of the kernelization complexity that extends also to subgraph closed and hereditary families F. Thanks for your attention.